Hello. So let's start one more lecture session on multivariate calculus integration. Now we had been discussing double integrals since past few sessions, and we have seen how to evaluate double integrals in different types of coordinate systems as Cartesian and polar, and how to evaluate double integrals in different kinds of regions. Now, today's lecture session, we will see application of double integrals in finding the area of a bounded region in the xy plane. And for this, let us remember that we have already seen if the function fxy is equal to 1, then the double integral fxy dx dy over a region omega reduces to the special double integral dx dy over omega, and this represents nothing but the area of the base region omega. This is because that dx dy gives you nothing but an elementary area, and as we are integrating over the region omega, we will get nothing but the area of the entire region omega. So let's now start to see some examples. So the first example here is find the area of the region R bounded by y equal to x and y equal to x square in the first quadrant. Now, of course, first we need to draw the region. So let's see it. So on the xy plane in the first quadrant, your region looks like this because this is your one boundary y equal to x and the other boundary y equal to x square, the parabola. So the region R is the one marked in blue. So to find the area of this region, as just now we have discussed, it can be given by the double integral dx dy. So what we need to do is to find the limits of x and y such that the region is covered. And if we treat the region as type 1 region, that means we will integrate with respect to y first. So what will be the limits of y? We see that if we take a vertical strip like this, the lower limit will be this lower curve y equal to x square, and the upper limit will be the straight line y equal to x. So y varies from x squared to x. And what about x? See that the minimum value of x is here x equal to 0, and the maximum value of x is 1 because the point of intersection of these two curves is 1, 1. So therefore we can now easily find the area. So the area will be now given by this repeated integrals, where we will first determine this inner integral with respect to y, where y, as just now discussed, will vary from x squared to x, and then we will calculate the outer integral with respect to x varying from 0 to 1. So integral of dy, it's nothing but just y. So as we put the limits from x squared to x, this gives us x minus x square as the integrand for the outer integral. And this we can easily integrate x square by 2 minus x cubed by 3. Your limits are from 0 to 1. So the final answer and the required area comes as 1 by 6. So let's proceed for one more example. Find the area of the region R bounded by the hyperbolas y equal to a square by x, y equal to 2a square by x, a greater than 0, and the vertical lines x equal to 1, x equal to 2. So let us draw the region once more. So it looks like this. These are the hyperbolas y equal to a square by x, and this is y equal to 2a square by x. And here we have the vertical lines marking the left and the right boundaries, x equal to 1 and x equal to 2. So this is our region R. And now it's very easy if we want to apply the double integral dx dy over the region R, because we can easily find the limits. If we first vary y, we see that if we take a vertical strip, the lower limit is nothing but a square by x, and the upper limit is nothing but 2a square by x. So we just put these limits, and the limits of x are already given. Basically, x varies from 1 to 2. So we are almost done. We have to just do the integration. So integral dy, that's again nothing but just y, and we put the limits. So this gives us 2a square by x minus a square by x, which is of course just a square by x. A square being a constant is taken out over here. So we just have the integral dx by x varying from 1 to 2. So dx by x is of course log x. So as we put the limits, we get a square log 2 minus log 1. And we know that log 1 is 0. So the final area is nothing but a square log 2. Okay, so let's proceed with one more example. But now we will see an example in polar coordinates. Find the area of one loop of the rose defined by the equation r equal to cos 2 theta. So how does this curve looks like and what will be the region? If you draw this one loop of the rose defined by this equation will look like this. Actually, you have another loop on the left hand side, but we have drawn only one loop. So, of course, we have to first find the limits of r and theta in polar coordinates so that the region r is covered. So for this, we usually take a radial strip like this. So if we take a radial strip, we will see the minimum value of r is of course 0 and the maximum value of r will lie on this curve. So it is nothing but cos 2 theta. So r will basically vary from 0 to cos 2 theta. And what are the limits of theta? As already shown here, we can see that theta will vary from minus pi by 4 to pi by 4. So the region we can now write as in this form, that set of points are theta, where r is varying from 0 to cos 2 theta and theta is varying from minus pi by 4 to pi by 4. And now, how do we write the area of the region in polar coordinates? See that in Cartesian coordinates, the area is given by the double integral dx dy. And we might remember that we have seen earlier that this differential dx dy in polar coordinates is given by r dr d theta. So therefore, the area will be now given by the double integral r dr d theta over the region r. And now we put the limits. So we integrate first with respect to r, and the limits of r as discussed are from 0 to cos 2 theta and the limits of theta are from minus pi by 4 to pi by 4. So as we integrate r dr, this is r square by 2. Limits are from 0 to cos 2 theta. And this, as we put the limits, this will give us cos square 2 theta and the half is taken outside. Now to integrate this function cos square 2 theta, let's write it as 1 plus cos 4 theta by 2. And now as we integrate this with respect to theta, we get theta plus sine 4 theta by 4 and outside we have 1 by 4 and the limits are going from minus pi by 4 to pi by 4. So we now put the limits and finally we will get the area as pi by 8 as we know that sine pi is going to be 0. So this is the final answer. Okay, so with this we will close today's session. In the next lecture class, we will discuss application of double integrals in finding volume of a region in the three-dimensional space. Thank you and goodbye till then.